understand when I tell somebody something and they hone in on just a single part of it instead of the whole overall point. It is easier math-wise.
That sounds like being a professor.
Right. I don't know how you do it. Skippy here.
I didn't say that.
I did. And Skippy is Noah Jameson Gray, for anybody that doesn't know or has listened to it before.
Oh, Lord.
The math is easy. The math's not hard. It's just like the last quiz we took. He's like, by the way, I screwed up on making it a problem, so it didn't make sense. Oh, yeah, I mean, you guys can figure it out. No, we can.
I'm not gonna touch that with a 10-foot pole.
Yeah, it's just I get confused as it is.
Okay, let's get started. In case it isn't apparent with my voice, I'm a little sick today, getting over some congestion and whatnot. But as I mentioned last week, I do plan on canceling class on Friday, and I figured I could either cancel class today and then make everybody come on Friday, or I could just muscle through it. So I'm muscling through it. Okay. So yeah. Okay. All the homework's graded, but exam 2 is not. As I mentioned, that's just going to be a spring break thing. Just being honest, that's just going to be a spring break thing. Because I've got this, and I have an exam in another class, which is on Wednesday. And I'll just do them all at once. So, sound good? Okay. How did the Excel homework go? Hopefully it was easy. I'm hoping. Well, okay. If there's any one lesson that I wanted you to learn from that homework, it would be this. As KL over R increases, what happens to capacity? Decreases. It decreases. And that's 100% true both with the math and the real world. I mean, what KL over R is slenderness, okay? It is a measure of how flimsy a column is. The bigger that value gets, the more flimsy it gets. And the more flimsy it gets, the more the capacity goes down, right? So here's a column. Its flimsiness determines how much load it takes for it to buckle. Does that make sense? Everybody okay with that? Okay, now my question today, and then we're ready to start doing some full bore problems, is the following, okay? So here's a column right here. Column on the ground, load. I take the load and I press it, and it buckles this way, okay? There's no real way, at least in its current state, for me to make it buckle this way, okay? Does that make sense? Like when I load it, it buckles this way. What if I wanted it to buckle like this way, along its strong axis as opposed to its weak axis? Does that make sense? See, I propose that in its current state, if I load this column just like this, the boundary conditions are the same along the top and the bottom, and the unbraced lengths are the same this way or this way. Because of that, there is no way that I can do this and it buckles about the strong axis. It's always buckling about the weak axis. And what I mean about the weak axis, if I take this and bend it, it's easier to bend it this way than it is this way. This is the strong axis. This is the weak axis. Okay? Now, how can we put some numbers to that? Well, that's what we're going to talk about today. So let's just recall that this is the capacity for a column, or specifically its critical buckling stress or its nominal buckling stress, F sub n. That actually changed from the last spec. Last spec it was FCR, now it's FN. But the math is all the same. So we take the slenderness. The first thing that we do is we compute an elastic buckling stress. The elastic buckling stress is not the capacity, it's just a parameter that we use to compute the capacity. Now really the only thing left to discuss is for a given column, what is KL over R? In other words, if I give you KL over R, you can do this. And if you can't, then you had a tough time with the homework, right? Because that's really what the homework was. Take a KL over R, compute this. Okay, now we got to determine KL over R. Okay, now K is pretty straightforward. It's a lookup, right? We just look it up based on table CA71. Remember, we use the recommended values, not the theoretical ones. The idea is that, so for example, for case A is a perfectly fixed column, but there's no such thing as perfect fixity with infinite rotational stiffness. It doesn't work like that, okay? Does that make sense? Okay. So let's talk about KL over R. Let's talk about the strong axis versus the weak axis, okay? So we want to be able to identify those axes and determine the controlling KL over R for a given column. And by controlling KL over R, or governing KL over R, I'm going to try and determine the largest KL over R, right? Follow that through. The largest KL over R is going to result in the smallest capacity, right? So for a given column, that's going to be what governs, okay? And you'll see what I mean. Okay. So first off, let's determine what I mean when I say strong axis versus weak axis. Okay, I want to take a step back and say that for now, between now and the rest of the semester, we are pretty much only going to be dealing in W shapes. And we are only going to be dealing in 50 KSI yield stress, 50 KSI yield stress. Just point blank, that's what we're going to be doing for the rest of the semester. That doesn't mean I'm not going to introduce you to some situations where that might not be the case, but all the problems we're going to be dealing with are pretty much W shapes with 50 KSI. Now, if you look at a W shape with 50 KSI, go find one in the manual. It doesn't matter, whichever one you find. Look at the RX and look at the RY. And you will always find that RX is bigger than RY. Now, I want to be clear. That is not always the case for every shape in the manual. That's not the case for every shape. For example, with WTs, you might find some WTs where RY is bigger. And obviously there are cases with angles where you have like a shape with a worst case scenario, like an unequal leg angle has an RZ. Okay, does that make sense? So I want to be clear that this isn't always the case, but for cases that exhibit symmetry like a W shape, more often than not RX is going to be bigger than RY. Okay, now because of that, we tend to refer to W shapes instead of x-axis and y-axis, we tend to use the term strong axis and weak axis. And again, when I say strong axis and weak axis, I'm talking about the axis about which we are bending, right? It is more difficult to bend an I shape this way than it is to bend it this way. I mean, that's why when we have beams in buildings, they stand upright like this. They don't stand like this, because this is how an I-beam wants to be bent, okay? And that's not only, just makes sense from a physics standpoint, it makes sense from the numbers. That's what Rx and Ry is. Remember, the radius of gyration is just a normalized moment of inertia. And the moment of inertia is what reflects stiffness, okay? Flexural stiffness, I should say. Now, let me just make a simple case for how bracing works, okay? So I need y'all's help on this. Okay, so I just made this problem up. Okay, let's just consider a W shape that is pinned on both ends. Okay, now when I say pinned on both ends, I'm talking about it's pinned on the bottom and it's pinned on the top and it's pinned on all directions. Okay, so I'm basically taking this and doing that. I'm doing exactly what I'm doing here with this little rubber I-beam. Okay, now let's just say for the sake of discussion that the column is 20 feet long, and I just went ahead and gave you some Rx and Ry values. Let's just say Rx is 6.2 inches and Ry is 4.1 inches. Let's see if we can determine how the column is going to buckle. And we're going to do that by looking at the slenderness values. Okay? So let's just sort of work this out. So the first thing that we're going to do is we're going to compute a KL over R for the x-axis, okay, which is really just going to be KXLX over RX. Okay? And some of you are thinking, why do you have this? Why do you have this going on? Why do you have the same diagram over here as you do over here? Don't worry, that's going to make sense here in a little bit. Okay? Whoop. All right, so 120 feet. RX is 6.20 inches. Does anybody see a problem with this?
The units aren't.
Yes. We're going to take that top one and convert it to inches by multiplying by 12. So what is 1 times 20 times 12 divided by 6.2? Because everybody brought their Casio FX 115 ES Plus or similar scientific calculator.
38.7.
Do I have a second on that? We'll just do 38.7. It doesn't matter. All right. So now we're going to do the same thing for the y-axis. And the only thing that's changing is R. Okay, and so what are we getting for this?
58.5.
58.5. Okay. So here's my point. Let's go back to what I was saying here. As capacity increases, as KL over R increases, capacity decreases. Why? Because KL over R is a measure of flimsiness. That's what slenderness is. It's how flimsy the element is across a given axis. I propose that for a given eye shape, if everything is the same across the x-axis and the y-axis, that because RY is smaller, this is always going to happen. It's always going to buckle this way and not this way. Does that make sense? Like, it's buckling like this, left to right. It's not going to buckle this way. Okay? Does that make sense? Okay. Now, does that mean that we... So I guess that leads to a question. Would the strong axis ever govern? I mean, would we ever honestly have to check the strong axis? Yes, it's very possible. Okay, because this is the point. Okay, what matters is not which is bigger, RX or RY. What matters is which is bigger, KL over R on the x-axis or KL over R on the y-axis. And to illustrate what I'm talking about, I want to look at this. Okay, here I've got a column that has different bracing conditions about the weak axis than it does the strong axis. Okay? For this column, I say that the strong axis is unbraced throughout its entire length because the only boundary conditions are at the bottom and at the top because that's what this beam here is doing. But across the weak axis, it's a different story. Across the weak axis, I got to brace here, got to brace here, got to brace here. I bet if I were to go to the new business building, I'd probably find columns like this in the main lobby. I'd have, like, across that exterior wall, I probably got columns or beams bracing this way, but not that way. Right? Does that make sense? I'm sure you've seen columns like that, like in the main lobby.
I'm trying to see if I can find a photo.
I'm sure there is, like, right there in that main lobby. So I want to see that here in a second. But the point I'm making is that the weak axis is split into multiple segments. Okay? Let me see. That's exactly what I'm talking about. Yep. So those columns there on the exterior wall. See, here, check this out. So here's what I've got for this problem. Okay, so I want to go back to this example, and I want to go back and say, what if we put a brace in the middle across the y-axis? Okay, so what I've done here is I've said, okay, let's go back to that original example, and let's say on the x-axis nothing changes, but on the y-axis, let's put a brace in the middle. Is it possible that the strong axis governs here? Let's see. So let's just make sure we're all clear. Same problem. The only difference is that now I've put a brace here. So how does it change things? Well, KL over R for the x-axis is still going to be 38.7. Like, that's not going to change. But what about KL over R for the y-axis? Well, we've got two segments. We've got a KL over R here and a KL over R here. Because here's my point. This segment, this is K is 1 and L is 10 feet. This one happens to be the same. So they actually, these two segments are going to have the same slenderness. It's possible that's not the case. We're going to do a problem here in a second where that isn't the case. But now we've got 1.0 times 10 feet over 0.1 inches. So what do we get here? .3. So now which way is this column going to buckle? It's going to buckle about its strong axis because it's more slender across the x-axis than it is across the y. What changed? We threw a brace in there. Okay. Did we make the column net stronger by putting in that brace? Yeah, we did. Because here is the controlling slenderness with the brace, and here is the controlling slenderness without the brace. So we actually made the column stronger by putting a brace in there. We decreased the controlling KL over R. So if we decreased the controlling KL over R, what happened to the capacity? It went up. Okay? Does that make sense?
What happens if those lengths are unequal? Like you didn't brace it in the middle?
That's a great question, and we're going to do a problem with that here in a second. I've got a problem where they're all different. Trust me, you're going to like it. The short answer is that's exactly what happens here. And we're actually going to do this problem here in a second. So we'll get to it, trust me. Okay. All right, does anybody have any questions about that idea of controlling slenderness? I had to have my little sound effect in there. I knew that's what you were laughing about. Okay, let's talk about analysis. Now, here's something that's a little different from what we've done before. I have multiple ways of analyzing columns. I can actually think of 3 separate ways to analyze a column. We're only going to use 2 of them in here, but I can think of 3. Okay? The first method is to just calculate it out, just to use the equations from section E3, which is what we're going to do. I'm going to call that method 1. Method 2 is to use a design aid. Okay? Now, there is a specific reason that I'm showing you method 2. Well, there are a few reasons. The first is that in order to design columns, we need a design aid. Okay? The math is too difficult. In other words, you can't just solve for A. Okay? And that's where, remember I told you, buying the manual, what are you buying? You're buying these design aids. So table 4.1a is the one we're going to use. And the difference is with 4.1a, 4.1b, 4.1c, they're just different yield stresses. Table 4.1a is so important, there's snippets of it in the FE reference manual. Like, again, you cannot design columns without it. Now, both of these methods are going to yield the same answer. Okay, I want to be clear. Analysis is analysis. The only difference between the two is rounding, like decimal trail off and whatnot. Like you might get 958.2 here and 958.6 here, and the only difference is just the analysis, because method 2 requires some linear interpolation. So the two methods serve as a check for one another. The math with method 1 is a little bit more intense, so if you do it independently, you should get the same answer. And again, you can't design without table 4.1a. And we're going to use a representative column on each method. So what is method 1? Method 1 is to just do what you all did on the homework assignment. So we're going to determine the controlling KL over R value. We're going to determine FE, the elastic buckling stress. Make sure that you're really careful with your units on KL over R. We're then going to compute FN and then compute VCPN. And I see a little typo there. That's supposed to be FN, not FCR. FNAG. Okay. So far, so good. You want me to give you all a sec to write this down? I see some of y'all writing it down. Sound good? Okay. So I want to do this example to address Mr. Moore's question. What happens if the segments are not even? Okay, well, here's one where they're not even. Okay? Now, we're going to analyze this column. This column is a 14 by 90. Okay, it's A992 steel. We're going to have different bracing lengths for each direction, and we're going to have a different K values for each direction. Okay? I want to determine the axial capacity of this column. Okay? So let's just sort of walk through this. And we're going to do this column twice, by the way. We're going to do it with method 1 and with method 2. Okay. Now, a couple things. For A992 steel, Fy is 50 KSI, and we do need some properties for the W14 by 90, okay? Now, specifically, we need 3 quantities. We need its gross area, which we'll use near the end, but we also need Rx and Ry. So somebody help me out. What is the gross area for a W14 by 90?
26.5.
26.5. Okay, what about Rx and Ry?
6.14, 3.7.
Okay. All right. Okay, everybody with me so far? Okay. So I want to take a look at this column over here, and I want to see if we can figure out what's going on. So here's the column in the real world. So this is an isometric view of the column. Okay. So I've got the x-axis fully unbraced, so I have a single 35-foot segment. So we'll call this segment X. Okay. For the y-axis, though, I've got 1, 2, 3. So we'll call this y1, y2, y3. So we got 3 different segments. Now let's see if we can determine what's going on with these segments, okay? Let's start off with the K values. Can anybody tell me, well, first off, maybe what we ought to do is turn to that K table, 16.1-650, I think it is. Let's see. Yeah, 650. It's way in the commentary, way in the back. So let's see if we can figure out what K value we should use. Let's start off with the x-axis. So we're pinned at the top, but the bottom is fixed. The bottom is fixed against rotation. So what K value should we use for x?
0.65.
Hold on. 0.8, because the top can rotate. Because everybody brought their AISC 16th edition steel construction manual, didn't they? I didn't say anything. Does that make sense? Why we're using that one? The bottom one prevents rotation, but the top allows rotation. Okay? What about Y1 and Y2? What's the deal with Y1 and Y2? We have a pin on top, pin on the bottom. Pin on top, pin on the bottom. What's the K value? 1, yeah. And what about the K value right here? What's it going to be? Pinned, fixed. 0.8. So, to address your question, Mr. Moore, what happens when you have segments that are of different lengths? The answer is you address all of them, okay? So, let's look at I don't think I plugged this fan up, and this thing's getting a little hot. There we go. Okay, so what I'm going to do is I'm going to write myself a little table. So I've got cases, and I'm going to say case X, Y1, Y2, Y3. Okay? For each of these cases, I'm going to write a K value. Okay? So my K values are going to be 0.8, 1, 1, and 0.8. And if you want, what I'll do is those are the cases. This is case B, case D, case B in that table. Okay, what about the lengths?
It's case C instead of case D.
What's that?
It's case C.
Oh, it is?
Yeah.
They,
No big deal, but
they must have rearranged it. Whoops.
the 0.8 would still be the ones in the middle.
Oh,
Sorry.
that was, oh, whoops. In the last manual, it was D. So, I thought I had updated that. Whoops. Thank you. Okay. Now, what about the L value? Okay. So, here's what I'm going to do for L. What about the x-axis? How long is that? Okay, so I'm going to say 35 feet is 420 inches. Okay. All right. Then we have 10 feet, 15 feet, 10 feet. So this is just me going ahead with the process of converting them to inches. Okay, does that make sense? Everybody okay with that? Okay. Now my R values, so maybe we'll put in inches here. Okay. What's my R value going to be for case X? It's an x-axis, so say it again.
6.1.
There you go. And what about the remaining ones?
3.7.
There you go. So, Now what we can do is compute a KL over R for each of these. So how do we do this row? 0.8 times 420 divided by that. 1 times 120 divided by that. 1 times 180 divided by that. 0.8 times 120 divided by that. And we're going to make an observation about this here in a second. Because I'm sure some of you have a question looming in the back of your head. And the answer to that question is probably yes. So somebody give me the first one. What's so funny?
Jerry said, yes, he's going to give us 10 grand each. That was my next question.
The question living in my head that you said the answer is yes.
Yeah, I must not have been that,
Telepathic.
telepathic. Yeah.
It's fine.
Say it again.
54.7.
54.7. So I'm going to track a couple different decimal points. I'm going to, and my main reason for doing that is just so later on in the problem you'll see where that value came from. Okay? If somebody could give me the next one, then I'll do the rest. What?
32.432.
Okay. I'll go ahead and do this one. And that one. So what do we do with these values? Somebody help me out. What do we do with these? You tell me. What do we do with them?
Choose the largest and that one governs.
Exactly. And so we end up going with this one. All right. Does that make sense? Okay. Now here's the question that has a yes to it. Notice how we did all three. Okay? And I'll get to my yes question in a second. But do we really need to do all three?
Yeah.
Okay, you're saying yes, you're saying no. Why are you saying no?
One of us is going to be right.
I don't have an answer to that. Let's look at the problem, okay? Slenderness is a measure of flimsiness, right? And we're trying to determine the segment that is the flimsiest. Let's just look at the y-axis. Which one is the longest? Y2, right? Which one has the largest k value? Y2, right? So, do we really need to check Y1 and Y3? Couldn't we have, by observation, just went, that's not going to matter? So my yes question is, hey, Dr. Mike, can we just ignore Y1 and Y3 on future assignments and just do the worst case one? Yeah. As long as it's apparent. That would be my stipulation. It's got to be apparent,
What about the fact that it has different k values?
Well, what I'm saying is they do have different k values, but this one has the largest k value. You see what I mean?
Yeah.
It's the largest k value and it's the largest length.
Okay.
So we could have just looked at it and known that along the y-axis, this had the largest, right? I'm still saying we need to have done this one too, okay? I'm saying that instead of doing all four, we could have done x and y too. And we really didn't need to do y1 and y3. That's what I'm saying. Does that make sense? Like I'm not saying it was a waste of time, but like now that you've seen what happens, my question is it a waste of time on the next problem, on the homework, on the exam? That's what I'm saying. Does that make sense? Okay. All right. So now that we have KL over R, we can compute the capacity pretty easily. And I'm going to go through this kind of quick because I'm hoping that this should be pretty simple given the homework assignment you just did. So we take pi squared E times KL over R squared, which is, man, my screen is dancing a bit today. And so KL over R, this whole term is just 54.723, right? And so chug that out and you get, I'll go ahead and do that one for you. 95. .578 KSI. Now, FE is not the capacity. FE is just a term used to compute the capacity. And how does that work? We take KL over R. And we compare it against something. Do you remember what we compare it against? .71. There you go. Okay, and what do we get here? This one I'll do for you, but the next one I want you to do. This one will get 113.43. So I have this value and this value, and I'm finding that KL over R I'm finding that KL over R is less than 4.71 square root of E over Fy. So let's just sort of recall. Are we in inelastic buckling mode or are we in elastic buckling mode? Y'all remember?
You said it was less than?
It'd be elastic.
No, hold on.
Inelastic. I don't know.
It's right on the line.
No. Remember right here? This is KL over R, right? Right here. So this is 4.71, and we're right here, right? So we're in inelastic buckling mode. So our capacity is computed according to this. So So our nominal capacity is 0.658 raised to the Fy over Fe times Fy. This one I want you to do. And remember, that's an exponent. That's not a, you're not multiplying by that fraction. It's 0.658 raised to that fraction. So that fraction looks like it's going to be about like 0.49, 0.48. So, bless you. It would be 0.658 raised to that. And then that times 50. Do I have a second on that? Okay. So therefore, and what is AG? Remind me. Making sure everybody's awake. Okay, and so what do we get for this? We'll keep it to 1 decimal place for this. Is that good? Do I have a second? All right. Okay. By the way, in design mode, most columns are going to use this. Most columns are going to be governed by inelastic buckling, not elastic buckling. Okay? Because inelastic buckling allows for more stress on the members, right? If you're in design mode, you want to use the smallest section possible. So if you want to use the smallest section, you're probably going to see a lot of stress, right? So that's why inelastic buckling is going to govern. And the same thing is going to be true for beams when beams buckle. We're going to be in zone 2 there. You don't know what I mean by zone 2, you will later. Does that sound good? All right. Now I want to show you something real quick while it's on my mind. So, just so you are aware, this is going to be your homework assignment, but I want to be clear that your homework assignment is going to have sort of a part 1, part 2 to it, okay? So what I mean by that is I'm giving you a homework assignment today that is due Wednesday, okay? I'm giving you this column, okay? Now, just so everybody's clear on the symbols, okay, for the x-axis, this cannot translate, but this can, okay? This is prevented against rotation, but it's allowed to translate, okay? Is everybody with me on that? So, no rotation, no translation. No rotation allows translation, okay? And everything on this axis is penned. Okay. I am giving you this problem today, due Wednesday, basically done the way we just did it. But this is analyzing columns using method 1. What about method 2? Well, on Wednesday, I'm going to give you the same problem, analyzing using method 2. Okay? Does that make sense? So it's the same problem, you're just doing it a different way. So far, so good? Now, what is method 2? Method 2 is using the manual. Okay? So bring your manual on Wednesday. Okay? And I kind of want to explain a little bit about method 2 with the rest of my time. But before we move on, does anybody have any questions about this? Hopefully this was pretty straightforward. Okay. This is method 2. Method 2 is to use one of the design aids. Okay? Now, this is table 4.1. Okay? There's a 4.1a, a 4.1b, and a 4.1c. We're going to use 4.1a since 4.1a is built based off of a yield stress of 50 KSI. Okay? The 4.1b and the 4.1c are just different yield stresses. As you saw in the last example, some of the calculations are a bit laborious. They're a bit intense. Okay? Table 4.1a makes our life a lot easier. Okay? What this table does is essentially list the capacities out. Okay? So if you look at the way it's organized, okay, so the very top will list the family of shapes, right? W12s, W10s, etc. Okay? Then it lists the second value, so W12 by 96, W12 by 87, W12 by 79, W12 by 72, etc. By the way, when you look at table 4.1a, you're only going to find W14s, W12s, W10s, W8s. That's it. What about W24s? What about W33s? What about those? Why aren't we using those for columns? Well, W14s, W12s, W10s, W8s are the ones that are the more square sections. What I mean by square is this dimension and this dimension are pretty close, okay? The reason why that matters is because the closer those dimensions are, the closer Rx and Ry are to each other, okay? Makes for a more efficient column, right? So columns are kind of square. Beams, on the other hand, are deep. Okay? So beams are going to be like W24s, W30s, W33s, etc. So when you look at table 4.1, you're only going to find square sections. Okay? That's what I mean by that. Now, how does table 4.1 work? Okay? Table 4.1, and if you have your manual with you, you ought to turn to it and you ought to read what's going on right here. Okay? Because this is probably the most important part. Okay? So what it says here is it says column capacity based on the axis with respect to the least radius of gyration Ry. Okay? So what it's saying is if you have a W12 by 79, for example, and the column has an effective length of 10 feet, and the weak axis governs, then if it's 10 feet, that's its KL. If its KL is 10 feet with the weak axis governing, its capacity is 932 kilograms. Done. Look up. But that begs a very obvious question. Well, Dr. Mike, what if the strong axis governs, right? Because very possibly, and as we just saw, the example we literally just did, the strong axis governs. So how do we use this table if the strong axis governs? Well, the way that we use it is we compute an effective KL, okay? And the way that that works is we say, okay, this table is built based off of KL over R in the y-axis. If we want to use KL over R for the x-axis, we need an effective KL. And the way that works is we set KLX equal to KL, or we set KL over R in the x-axis equal to KL over R on the y-axis, and we solve. And we do a little bit of algebra, and what do we get? We get that if you want to compute an effective KL, you take KL in the x-axis and you divide it by this Rx over Ry ratio. What do you see at the very bottom of the table? You see an Rx over Ry ratio listed?
Yeah.
Every shape has an Rx over Ry ratio already computed. Okay? So the way that it works, this is how column analysis works in table 4.1. Okay? So what you do for a column is you say, okay, I'm going to take, instead of computing, so what we did in our example just now, hold on. What we did in our example just now is we computed the worst case KL over R. Worst case KL over R in the x-axis, worst case KL over R on the y-axis. Okay? What we do with table 4.1 is it's a little bit more basic. With table 4.1, we say, all right, let's just look at KLs. Don't worry about the KL over R, just look at the KLs. And so we take a KL in the x-axis, a KL in the y-axis. Now, if KLY is bigger, or if KLY is equal to KLX, that means the weak axis is going to govern. Just look up the capacity. That's it. That's all you need to do. So that would be an example like this. Here's the example. Here's the column. Same bracing condition on either end. The column's 12 feet long, K value of 1. Just look it up based on 12 feet. That's it. But if KLX is bigger than KLY, what we do is we compute this KL effective, and we look up the capacity based on the bigger of either KLY or this new KL. And don't worry, we're going to have some practice about this on Wednesday. Now, there is a good chance what's going to happen is you're going to be looking up the capacity based on an effective KL of 14.62 feet. Well, there is no listing for 14.62. There's a listing for 14 and a listing for 15. So if you have the 14 value and you have the 15 value, how do you find the 14.62? You use this. Remember this? What was this, Engineering 111?
15 is good enough.
No. You interpolate, good sir. Although I appreciate that you're leaning the right way and going with the higher value. I do appreciate that. But no, you interpolate. So we use linear interpolation to compute the capacity. So just to explain, we're going to do this on Wednesday, but I'm going to take this problem and we're going to do it using linear interpolation. Okay? So we're going to use table 4.1 to do the problem we just did and see if we get a similar capacity. What will happen is we should get the same value. but it's going to be a little off due to the rounding, due to the fact that we are linearly interpolating a curve that's nonlinear. So there's going to be a little bit of decimal errors. But other than that, we should get the same answer. Sound good? My apologies, I kept you 1 minute over, but I'm going to stop the recording.